Hi, my name is Maggie Monahan, and this is my Physics 2212 Lab 4. The goal of this lab is to predict behavior of circuits with resistors in parallel/series, to measure conventional current and potential difference using ammeters and voltmeters, and to examine the behavior of resistors and capacitors. We will do this by first downloading the circuit construction kit on our laptops. Then, using this software, we'll drag and drop components of circuits in order to fulfill the instructions given. Then we will use these components to observe the circuit and record values, and finally, use these values to perform calculations. We will use the following physics principles in this lab. First, the idea of energy conservation, which says that energy cannot be created or destroyed. And with this, the loop rule, which says that the sum of voltage difference across a closed system equals to 0. Next, we will also use current conservation, which says that the total charge in an isolated system is constant. We will also use Ohm's law, which states that voltage is equal to current times resistance. The first circuit we built in this lab is a basic circuit containing two 1.5 volt batteries, an ammeter, and two resistors, one with 47 ohms and one with 100 ohms. Then we used a voltmeter in order to determine potential difference across different parts of the circuit. In this circuit, the ammeter read 0.02 amps, and the potential difference measured using the voltmeter was negative 9.59 volts across the resistor with 47 ohms, negative 2.041 volts across the resistor with 100 ohms, and 3 volts from above and below the batteries, and 0 volts on either side of the ammeter. This satisfies the loop rule, where the sum of the potential difference is equal to 0. Here you can see a graph of potential difference versus position on the circuit. As you can see in this circuit, it reaches the highest amount of voltage across the batteries, and then declines across the resistors. We can now use Ohm's law in order to determine the resistance by taking the change in voltage divided by the current. The resistance of the resistor with 47 ohms is equal to 47.95 ohms. The resistance of the resistor with 100 ohms is equal to 102.05 ohms. And the resistance of the wire and the ammeter are both equal to 0. In the second circuit, I used either a 10 or 20 ohm bulb, one 9 volt battery, and a 200 microfarads capacitor in order to time how long it takes for the capacitor to charge and discharge. For the charging capacitor, the bulb starts bright and then dims, and the current decreases. It was timed that it took 7.6 seconds for the light bulb to dim for the 10 ohm bulb and 14.6 seconds for the 20 ohm bulb. For the discharging capacitor, the 9 volt battery was taken out, and it was timed to see how long it takes for the capacitor to discharge. It took about 8 seconds for the 10 ohm bulb and about 15.1 seconds for the 20 ohm bulb. In the third circuit, a similar process was used to create the previous ones. However, this circuit includes one 9 volt battery, a 200 microfarads capacitor, and a 30 ohm light bulb. This circuit will be used in order to graph voltage versus time. Here you can see the voltage versus time graph, and you can see that it decreases exponentially. To do this, I stopped the simulation every second for 20 seconds once the battery was disconnected and the capacitor began discharging. Then, this data was transformed by taking the natural log of voltage divided by the initial voltage versus time. As you can see, this graph is decreasing with a slope of negative 1.66. However, we know that slope is equal to negative 1 divided by RC. Using this, we can find the RC constant is equal to 6.024 seconds. Finally, there are a couple of questions associated with this lab. First, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it affect the circuit you hooked it up to? If a real-life ammeter was used, the results would have been lower because real-life ammeters have some resistance. In the CCK simulation, this is an idealized scenario, and therefore does not have the resistance that it would have in real life. The second question is, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? And would this prediction happen in real life? The capacitor would not have reached full charge as quickly because there is some internal resistance. Thank you so much for listening.